Good morning. I'm assuming it's morning, perhaps it's not. We are now getting to the part where the rubber meets the road with respect to connecting all of this architecture we've built up directly back to what we measure experimentally in the lab. And before we get into Jones tensors, it makes sense to briefly review Jones vectors and matrices that form the foundation upon which Jones tensors are described. And so that's what we'll do right now. All right. So a Jones vector is a concise way of describing the complete polarization state of a purely polarized beam, now a plane wave. And by purely polarized, I don't mean it's either vertically or horizontally polarized. I mean it has a well-defined polarization state. And that's to contrast that with respect to something that would be partially polarized, like a light from an incoherent source. So if we have a purely polarized plane wave propagating in the z direction, then we have polarization components in the x and y directions. And so we can describe this as the Jones vector, where we have both amplitude and phase for both the x and y components of a propagating beam. And I'm showing this in this exponential form, which is the most common way of representing it. Simply, you can represent that phase shift by a complex term, and we can, if we have a phase shift in x and y, we can pull out all the common elements in this equation, reference with respect to the little delta x, and come up with one phase shift between the x and y. And it turns out that that's important. It's important because as long as we know that phase shift between the x and y, we can determine the polarization state. Now, usually we don't care about the absolute phase of an optical beam. We really only care about the relative phase. In other words, what is the phase difference between x and y? That's what defines the polarization state. And that's why we can pull out the absolute phase of one of those and describe everything in terms of the phase shift. So the Jones vector, if we normalize it, then it's a really concise and simple way of keeping track of what's going on with respect to the polarization state. And normalization is pretty straightforward. That's what's going on with this whole mess right here, which I won't go into in detail. I think I'll skip straight, you can find this in a lot of other places, but I'll skip straight to some common polarization states and what their representative Jones vectors look like. For horizontal polarization, it's, oh, come on, beam. Optics, I'm thinking beam. All right. For horizontal polarization, if the x position is defined as the horizontal coparallel with the horizontal axis, then it's simply 1, 0. Vertical is 0, 1. When it comes to right circular and left circular polarization, yeah, it turns out there's, not surprisingly, two separate conventions for the definition of right circular and left circular, and they invert. And that has to do with whether you're talking about a beam propagating, if you're referencing with respect to the optical axis, where your thumb is pointing, your right thumb is pointing along the pointing vector of the beam, then the definitions of right and left are shown here. And that's what we'll be using exclusively throughout any reference to polarization states in anything that I'll be presenting. However, if you're thinking about a fixed reference frame and looking at the optical path pass you by, then the same right-hand corkscrew motion would actually be described by the bottom expression and vice versa. So they invert depending on your reference frame. But again, we'll be focusing on a reference frame defined relative to the optical axis of the beam as opposed to a stationary reference frame. My apologies that there's two conventions. I can't do anything about it. Okay, Jones matrices allow you to convert. They are polarization transfer matrices. You can think of these just like any other transfer matrix. You put something in, you get something out. And as long as you know all the elements of M, you can predict what the complete polarization state that you would get out for any incoming polarization state, En. And we'll go through a couple of very common ones. A half-wave plate has this form. Now this is, I should mention, this is the Jones matrix for the half-wave plate with the fast axis aligned along the x-axis. If we rotate the half-wave plate, we'll show how to do that by introducing a rotation matrix. Quarter wave plate, again, you have to bear in mind the definitions of right and left circular polarization, which also affects the definition of the quarter wave plate. But in the reference, with the definitions that we are using, the quarter wave plate has this form, 1, 0, 0, I, where I is the square root of -1. A perfect mirror looks just like a half-wave plate. And an angled window, or an interface, has two Jones matrices, one describing the reflected component and one describing the transmitted component. And those are, this is a very general form. As long as there's no mixing between the P and the S, then it's just a diagonal matrix with the reflection and transmission coefficients along the diagonals. So those are not nearly as useful or as interesting as the Jones matrix for a rotated wave plate, for example. So if we want to rotate a matrix and describe it in a different reference frame, how do we do that? Well, it's the same thing that we did before. We can introduce a rotation matrix. So if we just have a single axis of rotation about phi, azimuthal rotation only, consistent with rotation about the z-axis, the optical axis, then the rotation matrix is just this matrix right here. And again, I'll point out that this is the intrinsic rotation defined here, in which the coordinate system is rotated relative to it. That's different than the rotation matrices where we're doing projections that were described previously. So you have to pay a little careful attention to how you're doing the rotation matrices and what they are, what they're meaning, and how you're defining the rotation of phi. In other words, if you define phi to be relative to the optical axis in terms of a projection, or if you define it to be relative to the reference frame of the optical beam, you come up with different values. Never mind. I'm rambling. All right, so if this is the rotation matrix, then if we want to describe a rotated half-wave plate, then the way to do it, one way to do it, is to rotate the reference frame to that of the half-wave plate at 0 degrees, and then rotate back to the laboratory frame. And that's sort of the classic way of rotating Jones matrices by this sandwich approach, where you have one rotation matrix and then the inverse of that rotation operation on the back side. And that gives this expression for a rotated half-wave plate, rotated some angle phi. You can similarly go through the analysis and come up with the rotation matrix of a quarter-wave plate. Again, we can, if we want to generalize it, the sandwich architecture is not as convenient as the projection architecture. In the projection architecture, we can describe this rotated half-wave plate by taking a Kronecker product of the rotation matrix with itself, and then multiplying that by the vectorized form of the Jones vector, of the Jones matrix. And this allows us to describe the architecture that is sufficiently general to extend to nonlinear optical measurements and rotation of tensors, because this can now be extended to arbitrarily high orders of optical interactions for Jones tensors. And you get exactly the same thing if all goes well. I won't go through the math because hopefully you'll be convinced just by my saying it that you do indeed get the exact same rotation matrix. Here it is in the vectorized form, and then if you reassemble it into a matrix form, then you get the same rotation matrix back. And that's the same architecture we'll be using for rotating tensors, and have used for rotating tensors. All right, that's the introduction. The next topics will be extending into the realm of nonlinear optics.